Here's the fourth and final lesson of the Linear Systems unit. I'm going to take you through 6 application questions, where in each of the questions there are going to be 2 unknowns that we're going to have to solve for. And to solve for 2 unknowns, you have to make 2 linear equations that involve both of the unknowns to be able to solve for their unknown values. And as we go through each of the questions, we'll follow these 5 steps I have listed here. Step 1, we'll assign variables to each of the 2 unknowns. Step 2, we'll then write 2 equations showing the relationships between the variables. And in each equation, we should include both of the unknown variables. Step 3, we'll solve the system of equations using any method, either substitution or elimination. I don't think we'll solve any of them by graphing. Then we should check the solution and clearly communicate the final answer. Let's try these steps with the first example. The first example says to find the value of 2 numbers if their sum is 13 and their difference is 5. So we should start this question by figuring out what are the 2 unknowns and then assigning them to variables. The question says find the value of 2 numbers. So we need to find the value of 2 different numbers. Let's let x equal the value of the first number, and let's let y equal the value of the second number. And now what I have to do is make 2 equations that involve the variables. So I need to make 2 equations that show the relationship between x and y. Well, I know that their sum is supposed to be 13. So if I were to add the numbers, x plus y, it should equal 13. That's my first equation. And then I also know that their difference is supposed to be 5. So my second equation would be that x minus y should equal 5. And now that I have my 2 linear equations that involve the 2 unknown variables, I can solve the system of equations using any of these methods. Based on the format of these 2 equations and the fact that the x's already have the exact same coefficient, I think elimination would be easiest. Let me start by stacking the 2 equations on top of each other, and then if I were to subtract the 2 equations from each other, the x's will eliminate. When subtracting the like terms, x minus x is 0, the x's eliminate, y minus negative y is 2y, and 13 minus 5 is 8. I'll divide the 2 to the other side, and I figure out that y is 4. And now I know what y is equal to. I can sub that back into either of my original equations to solve for x. I think I'll sub it into the first equation. I'll replace y with 4, and then I'll subtract the 4 to the other side, and I figure out that x is 9. Algebraically, x being 9 and y being 4 is the only pair of values that satisfy both of the original equations. Or graphically speaking, if I were to graph these 2 linear relationships, they would intersect at the point x equals 9, y equals 4. But in the context of this question, x is just the first number, and y is just the second number in a pair of numbers that have a sum of 13 and a difference of 5. And 9 plus 4 is 13, and 9 minus 4 is 5. So we do have the correct answer, we just have to clearly communicate it. I'll just say that the 2 numbers are 9 and 4. Now let's move on to our second question. In example 2, it says the sports shop sells Nike running shoes for $82 a pair and Air Jensen basketball shoes for $95 a pair. One day, the sports shop sells 75 pairs of Nike and Air Jensen shoes, totaling $6,241 in sales. How many pairs of each shoe were sold? So remember, we like to start by figuring out what are the 2 unknowns in this question. Well, it says how many pairs of each shoe were sold. So we're looking for how many pairs of Nikes were sold. We'll let the variable x be the number of Nikes sold. And we'll let the variable y be the number of Air Jensens sold. And what I need to do now is make 2 equations that show the relationship between these 2 variables. Well, I can make one equation based on the total number of pairs that were sold. It says on one day they sell 75 pairs in total. So my first equation would be that x plus y would equal 75. And then the second equation will be about the total dollar value in sales that the store has. They sell a total of $6,241, and I know the cost of each type of shoe individually. The Nikes sell for $82 a pair, and the Air Jensens sell for $95 a pair. So if I multiply the number of Nikes sold by how much each Nike costs, 82, so 82 times x, and then to that I add the number of Air Jensens sold times how much each air Jensen costs, so 95 times y, that should equal the total amount in sales that the store had, $6,241. And there's my second equation. Notice in each of these two equations, we have our two unknowns, x and y. So I can solve this linear system. Since, for example, one we did elimination, how about for this example, I'll use substitution. When I do substitution, I'd like to write the equations beside each other, and then I pick one of the variables in either equation to isolate. I think I'll isolate the x in equation 1. Since its coefficient is 1, it'll be easy to do. I'll just subtract this y to the other side. And since equation 1 tells me x is equal to 75 minus y, I can let the x in equation 2 equal that same value, and then solve for the value of y that lets their x's be equal. So I'll do the substitution of 75 minus y in for the x into equation 2, and now I'll just solve this equation for y. I'll distribute the 82 to both the 75 and the negative y. I'll collect my like terms. On the left, negative 82y plus 95y is 13y. And then when I take the 6,150, subtract it to the other side and collect it with the 6241, I get 91. And then dividing that 13, 91 divided by 13 is equal to 7. And since y stands for the number of air Jensens sold, I know that the store must have sold 7 pairs of air Jensens. To solve for the number of pairs of Nikes, I'll take that 7 back into equation 1 and replace y with 7. And that tells me that x is equal to 68, which means that 68 pairs of Nikes were sold. So I'll clearly communicate this answer. Therefore, they sold 68 Nikes and 7 air Jensens. And then, of course, you should check your final answers of 68 and 7 by taking both of those values, subbing them into both of the original equations, and making sure it makes left side equal right side for both of them. I won't show you that checking, but just make sure you know that you can do that for these questions. And now let's move on to example 3. Example 3 says a blue spruce tree grows an average of 15 centimeters per year, and an eastern hemlock grows an average of 10 centimeters per year. When they are planted, the blue spruce is 120 centimeters tall, and the eastern hemlock is taller. It's 180 centimeters tall. After how many years after planting will the trees reach the same height, and how tall will that be? Well, we need to start by figuring out what are our two unknowns for this question. Usually at the end of the question, it'll state what your unknowns are. Notice it says after how many years after planting will the trees be the same height, and what will that height be? So our two unknowns are the number of years after planting. So I'll say let x be that number of years, and I'll let y be the height of the trees. And now I have to make two equations that show the relationship between those variables. And since it tells me about two different trees, I should be able to make an equation about each of the trees' heights. The blue spruce grows an average of 15 centimeters a year, and it starts off at a height of 120 centimeters tall. So its total height, which we're defining as y, would be equal to its initial height of 120 centimeters tall, plus it's going to grow an additional 15 centimeters every year. So I can add 15 times the number of years, which we've defined as x. And that equation, which I'll call equation 1, gives me the total height of the blue spruce tree x years after it's been planted. And then if I make an equation for the height of the eastern hemlock, I know the eastern hemlock grows at an average of only 10 centimeters per year, but it does start off at a taller height when it's planted. It starts off at a height of 180 centimeters. So its total height, y, would be equal to its initial height, 180, plus it's going to grow 10 centimeters every year, x, after it's been planted. Now with these two equations that involve our two unknowns, we can solve the system with either substitution or elimination. And since y is already isolated in both of these equations, I think substitution is pretty straightforward. I'll write the two equations beside each other, and now I'll take what equation 1 tells me y is equal to, and replace the y in equation 2 with that. I'll change it to 120 plus 15x. So essentially, I've just set their heights equal, and now I'll solve for what value of x, what amount of time in years, makes their heights equal. I'll move the variable terms to the left side of the equation, and the constant terms, I'll move to the right side of the equation. And then when collecting my like terms, I find that 5x is equal to 60, and then dividing the 5, x equals 60 over 5, which is 12. So I know after 12 years, their heights will be the same. But what is the height? Well, just take this answer for x, sub it back into either original equation, I'll sub it into equation 1, and then solve for y. 15 times 12 is 180, add that to 120, I get 300. So these two values of x and y are the only pair of values that satisfy both of the original equations. Which means graphically, this point, the point 12, 300, is where they intersect. That's the only time, 12 years after planting, where their heights are going to be the exact same. They're both going to be a height of 300. So I'll write that in a sentence. And then if we wanted to verify this answer, we could actually graph both of these lines in Desmos and check and make sure that's the correct point of intersection. So if I graph the blue spruce and the eastern hemlock, I see the blue spruce started at 120, the eastern hemlock started at 180, but because the blue spruce grows faster, after 12 years, I see that they intersect. They intersect when they both have a height of 300 centimeters. And now let's move on to example 4. Tia had $10,000 to invest. She invested part of it in a term deposit paying 4% interest per year, and the remainder in bonds that pay 5% per year. If the total interest earned after 1 year was $440, how much did she invest in each account? Well, we'll start by defining our unknowns. We want to know how much did she invest in each account. So how much did she invest in the term deposit that pays 4%, and how much did she invest in the bonds that pay 5%? We'll let x equal the amount invested at 4%, and y be the amount invested at 5%. And then for all these investment type of questions, you'll be able to make two equations, one of them for the total amount invested, and one of them for the amount of interest earned. Let's start by making an equation for the total amount invested. Well, I know Tia invested a total of $10,000. So I know if I were to add the amount invested at 4% plus the amount invested at 5%, it should equal 10,000. So that equation's easy. My first equation is just x plus y equals 10,000. But my second equation is about the amount of interest earned. And I know that Tia earned $440 in interest. And based on the question, I know that 4% of whatever's invested in x plus 5% of whatever's invested in y should equal 440. Well, how do I figure out what 4% of x is? 4% as a decimal divided by 100, and I figure out that's 0.04. So 0.04 times x plus 5% of y, so 0.05 times y, should equal $440. And there's my second equation. Now that I have two equations with my two unknown variables, I can solve using substitution or elimination. I think I'll do elimination this time. We did substitution for the last couple, but I don't really like these decimal values. So how about I'll take equation 2 and multiply it by 100 to get rid of those decimal values. And then in equation 1, I'll want either the x's or the y's to have the same coefficients of that x and that y. So why don't I multiply equation 1 by 4 so that the x's have the same coefficients? And when multiplying all three of these terms by 4, I get 4x plus 4y equals 40,000. And then subtracting these two equations from each other will eliminate the x's. It will give me y equals 4,000. So I know the amount invested at 5% is $4,000. Take that answer for y, sub it back into either original equation. I think I'll sub it into 1, and I'll be able to solve for x. So I'll replace this y with 4,000 and subtract that 4,000 to the other side, and I figure out x is 6,000. So the amount invested at 4% is 6,000, and the amount invested at 5% is 4,000. I'll write that in a concluding statement. And now let's move on to example 5. This one is a classic linear system example. We have a chemistry teacher that needs to make 10 liters of 42% sulfuric acid. The acid solutions available are 30% sulfuric acid and 50% sulfuric acid. How many liters of each solution must be mixed to make that 42% solution? So somehow we need to mix a certain amount of 30% and a certain amount of 50% to make 10 liters of 42% sulfuric acid. Well, our unknowns are how many liters of each of these different solutions. So we'll say let x be the amount of 30% sulfuric acid, and y can be the amount of the 50% acid mixture. And for these mixture questions, we're going to always make two different equations. One of them for the total volume of the solution, and 1 for just the amount of pure acid that's in the mixture. So this question is actually really similar to that investment question. Let's start by making our total volume equation. Well, I know that the teacher needs to make 10 liters of a mixture. So I know whatever amount of the 30% acid plus whatever the amount of the 50% acid should add up to 10. So I can say that x plus y equals 10. And then for my equation for the volume of pure acid that's in the mixture, well, only 42% of the 10 liters should be acid. So the amount of pure acid is 42% of 10 liters. But what is 42% of 10 liters? Well, 42% divided by 100 is 0.42. If I multiply that by 10 liters, that will tell me the total amount of sulfuric acid that is within that 10-liter mixture. And I know that total amount of acid, I can set that equal to, well, 30% of mixture X plus 50% of mixture Y will give me this total amount of acid that's in the mixture. To find 30% of X, change 30% to a decimal by dividing it by 100, and that gives me 0.3. So 0.3 times X plus 50% of Y, so 0.5 times Y. The sum of those two will give me the total amount of acid that's in the mixture, which should equal 4.2 liters. And now that I have these two equations, with my two unknowns, I can solve using substitution or elimination. Let's do elimination again. Let me start by getting rid of these decimals by multiplying equation 2 by 10. And then in equation 1, I'm going to multiply it by 3 so that my x's will have the same coefficients. Multiplying all three of these terms by 3 gives me 3x plus 3y equals 30. And notice because I'm doing elimination, I made sure to write these two equations in the same formats, having their like terms lined up in columns. And now subtracting these two equations will eliminate my x. 42 minus 30 is 12. 3x minus 3x is 0, it's eliminated. And 5y minus 3y is 2y, which means if I divide the 2 over, y is equal to 6. So I know the teacher must be using 6 liters of the 50% acid, and then taking that answer and subbing it into either of my original equations. I'll sub it into equation 1. I know that if there is 6 liters of the 50% solution, subtracting that 6 over, I would find out that there are 4 liters of the 30% solution. So I can state that final answer in a nice sentence. And now let's move on to the last question of this lesson, where it says a riverboat took 2 hours to travel 24 kilometers down a river with the current, and 3 hours to make the return trip against the current. Find the speed of the boat in still water and the speed of the current. So our two unknowns, it tells us right at the end, what's the speed of the boat in still water and what's the speed of the current. I'll let x equal the speed of the boat in still water, and y can be the speed of the current. What I have to do now is write two equations that show the relationship between those two variables. And since the question gives me information about time, distance, and I'm solving for speed, I know the relationship between those three things based on this equation here. Distance is equal to speed times time. So if we look at what I highlighted in blue, that's the trip where the boat is traveling with the current. I can make an equation from that information. When traveling with the current, the distance traveled is 24 kilometers. So using this equation, I can set distance equal to 24, and that distance would equal the boat's speed times the time. Well, I know the time. It says it took 2 hours for that trip. So I can do 2, and I have to multiply that by the boat's speed. And when it takes 2 hours to travel 24 kilometers, it says the boat is traveling with the current. So the speed will be the speed of the boat traveling with the current, which will be the speed of the boat in still water plus the speed of the current, right? The current is going to help speed up the boat. Someone watching from the shore will see the sum of those two speeds. So I can add x and y together, the speed of the boat in still water plus the speed of the current, which will give me the total speed of the boat with the current for this section of the trip. So I can set my speed to x plus y. Notice in this equation, we just have the distance equals the time multiplied by the speed, which comes from this equation. And then let's do the same thing, but for the return trip, which took 3 hours to travel the same distance, but this time against the current, which is why it took longer. So this time, to get the speed traveling against the current, since the current is working against the boat, we would calculate that by doing the boat speed minus the speed of the current. So the speed for our second equation is going to be x minus y. But we're traveling the same distance. So in the second equation, the distance is still 24, but it takes 3 hours because the speed of the boat against the current will be the speed of the boat in still water minus the speed of the current. And now with these two equations, we can solve using substitution or elimination. I think I'll do elimination again. And for each of these equations, before I do elimination, I could distribute the 2 and the 3, or I think what I'll do is for this equation, I'll just divide both sides by 2. If I divide both sides by 2, the 2's cancel, and I get 12 equals x plus y. And for equation 2, I'll divide both sides by 3. Dividing both sides by 3, those cancel, and 24 over 3 is 8. So I have 8 equals x minus y as my second equation. And I said I'll do elimination, so I'll stack the equations on top of each other. And this time, why don't I add these two equations, and the y's will eliminate. When adding the equations, 12 plus 8 is 20, and x plus x is 2x. And then dividing the 2, I figure out x is equal to 10. And then I could sub that value of x equals 10 into either original equation. I'll sub it into equation 1. Replacing this x with 10, 12 equals 10 plus y, subtract the 10 over, y is equal to 2. So I've solved that x, the speed of the boat in still water, is 10 kilometers an hour, and y, the speed of the current, is 2 kilometers an hour. So I'll summarize that in a concluding statement. And that's the end of all the examples we'll do in this section. To get good at these linear system applications, make sure you go to jensenmath.ca and get the free practice problems that go along with this lesson and try them out. Jensen Math.